Hello students, welcome to Go Vidya and welcome back to the 1000 important series questions on DC machines. Today we will discuss about the DC machine questions. Let's move to the first question. The first question. Consider the following statements: the use of interpoles in DC machines to counteract the dash. Which of the following? The first is reactance voltage. Second one is demagnetizing effect of armature MMF in the commutating zone. Third, cross magnetizing effect of armature MMF in the commutating zone. So which of these following statements are correct? So the use of interpoles in DC machines we have to know. Then what is the counteract? How to counteract it? Nothing but how to neutralize it. So before neutralizing with the help of the interpoles, we have to know what is interpole, what is the function of the interpole. In general, interpole is connected in series with the armature winding. Let's see the diagram. Stator, rotor. I am considering the two fields, north and I am taking a two pole, north, south. So this will be D axis. How to know this is a D axis? Whenever the induced EMF E is equal to 0, we say that as a D axis or polar axis. That is D axis or polar axis. So here the interpoles are located along the Q axis. Along the Q axis, the interpoles are located. So along the Q axis, the interpoles are located. We say this is Q axis or interpole axis. So here the EMF will be maximum. EMF will be maximum. Whenever the EMF is 0, we say that as a D axis or the polar axis. And whenever the EMF is maximum, we say it as Q axis or interpolar axis. Coming to this, interpoles are located along the interpolar axis or the Q axis. Next, so this is connected in series with the armature winding, and this is located along the Q axis and along the brushes. So it is said as brush axis also. So coming to the how to neutralize, what type of how to neutralize is that we can neutralize the reactance voltage and we can neutralize the cross magnetizing effect of armature MMF in the commutating zone. So how to neutralize it? How to neutralize the reactance voltage? Actually, interpoles also provides a voltage that which cancels, and also to cancel that reactance voltage, the voltage is induced in the coil, short circuited coil under the commutation, and the interpolar voltage it will cancel the both, and the reactance voltage will be cancels and it will become a very smooth in nature, and there will be a smooth commutation. Coming to the next, cross magnetizing effect of armature MMF in the commutating zone. See, in general, interpoles used to neutralize the cross magnetizing effect in armature reaction. In general, interpoles are used for the neutralize the cross magnetization in armature reaction. So the resultant flux will be 0. As the resultant flux will be 0 along the IP axis. So cross magnetizing and reactance voltage, not the demagnetizing. So the option 1 and 3. So let's move to the next question. A DC shunt motor is excited from an alternating power frequency voltage source. Brush axis is rotated by an angle alpha from the geometrical neutral axis. The torque developed will be proportional to which of the following? So we have to find out the torque developed which is proportional to. Before that, the brush axis is rotated by an angle alpha. Nothing but here it has been shifted. The angle has been shifted. In general, we know the formula torque developed torque developed, T is directly proportional to Fa Fm sin alpha. But here it has been shifted by an angle alpha. Sine shifted by an angle alpha, so we can write sine 90 minus alpha, which is nothing but cos alpha. So the brush axis has been shifted by an angle alpha, then torque will be directly proportional to the cos alpha. So the option B matches. Next question. In a DC machine running with a heavy load and with the brushes located on the GNA, geometrical neutral axis, sparking occurs at the brushes during commutation because of. So nothing but sparking occurs at the brushes during commutation because of. The reason we have to know. That is first one, A, the high current density at the coil ends. B, the centrifugal force exerted on the brush by the commutator. Option C, shifting of the magnetic neutral axis. Option D, the reduced main field flux density in the interpolar regions. In general, in a DC machine, the heavy load, the armature reaction becomes very strong. During the heavy load, the armature reaction becomes very strong. And this distorts the main field flux and the armature field flux. Main field flux and the armature field axis. Then the MNA will be away from the GNA. MNA will be away from GNA. This is when heavy load. This is when the heavy load MNA will be away from the GNA. MNA. Magnetically neutral axis, geometrical neutral axis. But if the brush remains at the same position, nothing but at the same GNA, instead of shifted of the MNA, it will become very poor. The commutation will be very poor. Coming to this case, the commutation will be better commutation. The commutation will be better if it is shifted. If it is not shifted, we will get the poor commutation. So in the question they have given a heavy load and the brushes are shifted also. So the option, the shifting of MNA, nothing but the shifting of the magnetic neutral axis. So let's move to the next question. The induced EMF of a DC machine at 750 RPM is 220 volts. The percentage increase in the field flux for generating an induced EMF of 250 volts at 700 RPM is. So we have to calculate the percentage increase in the field flux. Yes, we know the formula. E is directly proportional to phi n. So I'll write directly E2 by E1 is equal to phi 2 by phi 1 into N2 by N1. In the question they have given the E2, that is 250 volts, and E1 is 220 volts. So we have to find the change in phi 2 and phi 1, nothing but the change in the flux. The speed 250 700 RPM, and N2 is 700, N1 is 750 RPM. This is phi 1, 1.2177. So we have to calculate the percentage, nothing but change value, nothing but phi 2 minus phi 1. So we will get around 21.7%. So the option C matches with that. So E is directly proportional to phi n. We have to calculate the percentage change in flux. If they have asked in the question the same percentage in the speed, nothing but they will mention the value of the flux, we have to find the N2 by N1 value, percentage change, nothing but change in value. So let's move to the next question. In DC machines, the field flux axis and the armature MMF are respectively. So this field flux axis, so field flux will be from north to south pole, where the EMF will be 0. So if the EMF is 0, we can say it is along D axis, which is nothing but polar axis. So let's move to the first one. Field flux axis along the polar axis or D axis. Direct axis is option B, option C no, option D no. So the answer will be between A and B. Let's check that. Next, armature MMF. We know the armature MMF will be along the IP axis where the EMF is maximum. So armature MMF will be along the IP axis. So direct axis nothing but D axis and interpolar axis. So the option B matches. So clear? So the field flux will be from north to south pole where the EMF will be 0. We say that as a D axis or the polar axis. And coming to the armature MMF will be along the interpolar axis where the EMF will be maximum. So let's move to the next question. A DC motor running at 2000 RPM has hysteresis loss of 500 watts and eddy current loss of 200 watts. The flux is maintained constant but the speed is reduced to 1000 RPM. At the reduced speed, the total iron losses. So we have to find the total iron losses. So before finding the total iron losses, they are saying that speed is reduced to 1000 RPM and flux is maintained constant. We know in general speed is directly proportional to frequency. Yes or not? Yes. Directly proportional to frequency. But I have to calculate the total iron losses. Total iron losses means, can I write the hysteresis losses plus eddy current losses? Yes. Hysteresis loss plus eddy current losses gives the total iron losses. Let's find the hysteresis loss. This is total iron loss. So WH2 is equal to WH1 into F2 by F1. So 500 into 1000 by 2000. You will get around 500 by 2 is nothing but 250 watts. So the hysteresis loss we got at 250 watts. We will find the eddy current loss. W2 is equal to WE1 into F2 by F1 whole square. So WE2 is nothing but eddy current loss is nothing but 200 watts. So 200 into F2 is 1000 and this is 2000. So you will get directly 1 by 2 whole square is nothing but 1 by 4. So 4 into 50. 450 is 200. So W2 is 250 watts. So we have to find the total iron loss. So this is nothing but WH plus WE. Nothing but WH2 plus WE2. That is nothing but 250 watts plus 50 watts. We will get around 300 watts. So the total iron loss is nothing but 300 watts. So the option C matches. Don't confuse. They have given in the question speed is reduced, nothing but. So we have to see the relation between the speed and frequency or speed or poles or something. We have to check the relation. Directly they didn't give the data regarding the frequency, but they have given the data regarding the speed. So we know that speed is directly proportional to frequency. From there I have calculated the eddy current loss and the hysteresis loss. That is nothing but the total iron loss. Okay, let's move to the next question. A DC motor develops an electromagnetic torque of 150 Newton meter in an operating condition. From this operating condition, a 10% reduction in the field flux and 50% increase in the armature current is made. What will be the new value of electromagnetic torque? So we have to calculate the torque. So in that they have given 10% reduction in the flux and 50% reduction in the armature current. So we know the formula T is directly proportional to phi into Ia. But in question they have given phi 2 is 10% reduction means 0.951. So can I write 0.951 and 50% increase in armature current. So I can write Ia2 is equal to 1.5 into Ia1. So let's substitute the values in this. We'll get the new electromagnetic torque, and the T1, nothing but T1 is 150 Newton meter. So we'll substitute all these values. T1 by T2 is equal to 5.1 by 5.2 into Ia1 by Ia2. For simple calculation, what we do is we just reverse it. T2 by T1 is equal to 5.2 by 5.1 into Ia2 by Ia1. Let's substitute the values. I have to calculate the T2. I know the value of T1, that is 150 Newton meter, and 5.2 is 0.951. 0.951 by 5.1 into Ia2 is nothing but 1.5 Ia1 by Ia1. Ia1 will be getting cancelled. 5.1 and 5, this 5.1 and 5.1 will be cancelled. Now T2 is equal to 0.9 into 1.5 into 150. In total you will get around 202.5 Newton meter. So the new electromagnetic torque we'll be getting is 202.5 Newton meter. So the option 225 no, 22.5 no, option B 202.5 Newton meter. See, in exam you will be getting confused because you got the exact answer, correct result, that is 202.5, but in hurry burry or some tension you keep answer as a D, 20.25 Newton. You don't see where the point is located. So be careful while answering also. So let's move the next question. A 10 HP 240 volts DC shunt motor having armature circuit resistance of 0.5. So RA is 0.5 ohms and full load current of 40 amperes is started by a starter such that the sections of the required resistance in series with the armature circuit should limit the starting current to 150% of the full load current. So the steady state EMF developed by the machine at full load when the arm of the starter is moved to the next step. See, as the question is very lengthy, but don't afraid of that. Here very simple, we have to calculate the steady state EMF when the starter is moved to the next step. Nothing but we have to calculate the back EMF when the starter is moved. If this is the initial position, if the starter is moved to the next step, we have to calculate what is the EMF. Let's do that. We will find the starter current, that is 40 amperes into 150% of the full load current, that I can write simply as 1.5, which is nothing but 1.5 into 4, that is around 60. So we will find the resistance, starter resistance also. So in the question they have given the 240 shunt motor, 240 volts. So I can write 240 by 60, you will get around 4 ohms. This is the starter resistance. Now we have to calculate the back EMF, steady state EMF, that is back EMF, that is equal to 240 minus, they have given the motor not the generator, 240 minus 40 into 4. You will get 240 minus 160, that is 80 volts. So the option C matches. So let's move to the next question. A cumulative compound DC motor runs at 1500 RPM on full load. If it is series field is short circuited, its speed is. So in the question the series field is short circuited, its speed we have to calculate what is the speed. In general, cumulative compound is nothing but adding the shunt and the series field. Nothing but adding both shunt and series field. Nothing but 5SH plus 5SC adding. This is cumulative. But coming to differential, we will subtract the both shunt and the series field. Subtract both shunt and series field. 5SH minus 5SC. This is differential. we know the relation N is directly proportional to 1 by phi SH plus phi SC. In the question they have said phi SC is short circuited, which is nothing but equal to 0, which is nothing but flux has been reduced. The flux has been reduced because the series field is short circuited. If the flux is reduced, definitely the speed will be increased. If the flux reduces, the speed will increase. So the option A becomes 0, no. Speed becomes 0, no, it doesn't become 0. Remains same, no. Increases, yes, it increases. The speed will increase as the flux will be decreased. So thank you everyone.